pretty optimistic approach. We changed the subject more to a more threatening subject, at least in my estimation. Watching the Earth breathe sounds harmless in a certain way, but this talk describes the global effort to understand the largest global challenge, I think that's another word for threat, over the next century, the climate change. And the speech is done by Julia Marshall from Canada, but presently working in Jena at the Max Planck Institute for Biogeochemistry, Watching the Earth Breathe. Welcome, Ms. Marshall.
Great, thank you. All right, so yes, this is rather more focused on the physical sciences, so it's a bit of a different flavor, but I tried to make it hopefully understandable to a broad audience to give you an idea of what we're doing related to carbon cycle research to try and understand some of the drivers for the global change that we've been hearing so much about. Now, I've titled this Watching the Earth Breathe, because this is sort of how I think of it. When we breathe in oxygen and breathe out carbon dioxide. It's sort of what we know. With the Earth system, of course, there's an exchange of oxygen as well, but what I mean more is what happens on an annual scale, where we have the uptake of carbon dioxide as plants grow, and then as organic matter is decomposed, there's a release of carbon dioxide, and this has a certain seasonal cycle. What you see here in the figure is what we model it based upon observations, and what we think the concentration of carbon dioxide in the atmosphere looks like near the surface. And what you see, so you can see that there's a lot of yellow areas where there's industrial activity, and this is mostly anthropogenic emissions, but we're already getting now, so day 130, so we're kind of around, May, and so we're getting into the uptake period. This is when the plants start growing in the northern hemisphere. I've centered the globe directly over Jena, so you can see what it's like here. And you can see this wave of blue sort of circling the planet. And what this is showing us is really the plants growing as the sun, as daylight passes over the Earth. And this is the kind of global signal that we see of the carbon exchange in the atmosphere. This is the middle of the growing season, and you still see, if you look down towards the tropics, in southern Africa, you can see some yellow coming out. This is not a lot of burning of fossil fuels. This is actually the sort of natural cycle of fires, the savanna fires in this time period. At this point, you don't see any yellow in most of the northern hemisphere, a little bit over China still, because the signal from the biosphere, the land biosphere, the plants, really overwhelms what we see of the anthropogenic sources. But the anthropogenic, that is the man-made release of carbon dioxide, is certainly still there. So I'm going to talk a bit more about this in context and how we do this and why it's important and how it links to global understanding. So I'm going to start to put this in context with a figure that is from the 5th assessment report of the Intergovernmental Panel on Climate Change, And this is really showing why it matters that we're burning carbon dioxide. Everybody is worried about the climate changing, and I found this to be one of the most illustrative figures that, yes, it's enormously complex. Yes, there are lots of drivers and lots of feedbacks, but essentially what matters the most is how much carbon dioxide we're putting into the atmosphere. That's on this axis. And then how it relates to the temperature anomaly. That's on this axis. Now, in black is all we have of observations. That's up to 2010. And the other lines after that are based upon different emission scenarios. So based upon different economic models, different projections, how much carbon we might release over the next century. All of them show increasing temperatures, of course. And I should mention that the most optimistic of these, the dark blue scenario, is considered to be not really likely at this point. And the red line, which is much the worst, is sort of the business as usual scenario. And this is rather terrifying, but it also shows us that what matters most is how much carbon dioxide we put into the atmosphere. But luckily for us, a lot of the carbon dioxide we put into the atmosphere does not stay in the atmosphere. And this is where we get into the Earth part. So this is an overview of the global carbon budget. This is produced by the Global Carbon Project for 2015. It's a compilation of data from a variety of sources. What you see above the line is all of the sources. This is mostly fossil fuels and industry, including cement production. These are large sources of carbon dioxide. And as already been mentioned, after around 1960 is when we see the beginning of the great acceleration, when the rate of increase became enormous. So you see that it's getting larger and larger every year. The other main source is land use change, and this has to do with deforestation for the most part, so also agricultural practices. But it doesn't all stay in the atmosphere. If it all stayed in the atmosphere, then this whole part in the bottom would be this sort of gray color. But only about 45% stays in the atmosphere, which is good for our climate. The rest of it is taken up by the ocean and also by the land sink. The land sink has to do with forests growing and dying back, and a lot of what we're trying to do is understand this. As you can see here, the land sink is the most variable. It has the most interannual variability, and this is related to other climatic factors, things like El Nino, and so large weather patterns affect how much the land can uptake from year to year. This is a lot of the kind of work that we're doing at the Max Planck Institute for Biogeochemistry here in Jena. Now, we're doing this using measurements, in my department at least, in measurements from the atmosphere. Now, our longest record of the atmosphere, considering carbon dioxide, is from Mauna Loa. And we can get a lot of information from one measurement in one place for a long period of time. The sort of zigzag that you can see here, this is the Earth breathing. When it goes down, this is the northern hemisphere summer, and when it goes up, this is the northern hemisphere winter. It's dominated by the northern hemisphere, partly because Mauna Loa is on Hawaii, and this is in the northern hemisphere, but also because there's much more land in the northern hemisphere. So this part really dominates the signal. But you also notice that there's a massive trend in this line since 1960. And this trend is entirely to do with anthropogenic emissions of carbon dioxide. We can also get some information about the rate of change by looking at the changes in slope. So we already have a lot of information that we need to constrain sort of the state of the atmosphere from one measurement. But if we add more measurements, we learn that much more. Even just considering one further measurement at the South Pole and Antarctica, we can see quite a lot more. One thing is that the seasonal cycle is much, much smaller, and it's reversed in cycle, and that's because it's seeing the southern hemisphere, which has, of course, an opposite summer and winter period than the northern hemisphere. So this is already interesting. We can also see that around 1960, the mean of the two signals was about the same. And nowadays, they're quite offset, and that has to do with the transport time it takes from the emissions, which are mostly in the northern hemisphere, because most of the people live in the northern hemisphere, and it takes the emissions a few months to make it to the southern hemisphere. So we're already getting lots of information here. Now it's a question of how would we use this information. So we have measurement towers around the world, not just at Mauna Loa and South Pole, and we make a measurement at one and a measurement at the other. So let's say that at the first one, it's 400 parts per million. This is a kind of typical concentration for carbon dioxide in the atmosphere these days. And we measure downwind, and it's 410 parts per million. And we know there's a factory in between. So we put this information together, and if we know the wind speed and a little bit more about how the air is circulating, we can estimate the emissions. It sounds easy. It's mostly easy, but sometimes it gets more complicated. So for instance, here, if there's also a forest in between the two measurement sites, then we measure 400 parts per million, and the sun is shining, so there's photosynthesis going on, and we measure 400 parts per million downwind. So now it really is important for us to have some prior knowledge about what is in between our measurement sites. It helps to know that there are anthropogenic emissions and also biogenic signals. So we know that the forest is taking up something and the factories are releasing something. That's sort of the short version of how we're doing this. Now to have a look at what our observational constraints are, this is sort of the international network of surface stations that we have measuring carbon dioxide around the world. Of course, Mauna Loa is there. That's right over here. But we still don't really have global coverage, as you can see. Particularly South America, with a very, very large rainforest, is largely unmeasured, as is most of Africa, India. We don't have measurements in much of the tropics, and this is a problem. the network as it is already a collaboration between international institutions and laboratories working together to have common data standards. And it's quite impressive, but it has holes. In recent years, we've been working on trying to bridge this gap with the use of satellite measurements. And this is my particular region of study. So if you want to talk more about satellites offline, please find me. And so this is GOSAT measurements. This is from a Japanese satellite, and it's just showing the data coverage for 1 year. And you can see that it's giving us a lot more information. However, we're still missing a lot of information. The coverage travels up and down throughout the year because you need reflected sunlight to make this measurement, which means you can't make measurements in the wintertime, only during the summertime, essentially. And you can't make measurements when there's clouds. So we still don't have a lot of data over the Amazon and over the African rainforest. And so this is really still not perfect, but we're getting there. And then we put it all together in a modeling framework. And this is essentially what we come up with. Now here, this is the same plot as you saw before. This is the near surface carbon dioxide concentrations in parts per million. And then here it's split into the biogenic fluxes. So that is the ocean and land biosphere, uptake and release. And then the anthropogenic fluxes for 1 year. And the anthropogenic fluxes, in the red areas, you see this is sort of the source regions. So we see the source regions in Asia and Europe and North America. There are, of course, anthropogenic fluxes in the southern hemisphere as well, but they are so much smaller than what is going on in the northern industrialized countries that they almost don't show up. And as we see this over the course of the year, we see that the anthropogenic fluxes don't stay close to where they are. They're transported globally. They're transported, it takes some time to get all the way around the world, so you end up with gradients, but carbon dioxide is incredibly long-lived, so it stays in the atmosphere. This is in contrast to what we see for other atmospheric pollutants, I'll say. So if we consider nitrogen dioxide, this is something that's released, for instance, from car exhaust. So it happens when we burn fossil fuels, essentially. Nitrogen dioxide is a major pollutant. It contributes to photochemical smog. It makes the air unpleasant to breathe. It makes people sick. However, it doesn't last very long in the atmosphere. If we stopped driving cars tomorrow, this would disappear within a week or two. So this is a relatively short-lived pollutant. That means it also has a relatively short-lived geographic impact. We see on the news stories about how terrible the air quality is in, say, Beijing, and then we can go outside and breathe clean air. This is largely a localized problem compared to something like carbon dioxide. Also, in contrast to carbon dioxide, everyone realizes that the air is unpleasant to breathe, so it's easier to find the motivation, and immediate action results in immediate improvements. And we have seen improvements in the air quality in Europe and North America over the past 15 years or so because of changes in emission regulations. However, localized emissions have a mostly local impact for this type of air pollution. For carbon dioxide, it's really different. The very long lifetime on the scale of centuries means that emissions are distributed around the world. They don't stay where they're emitted. Localized emissions have a global impact. Even if you live somewhere and have an entirely self-sustaining, sustainable homestead and you're carbon neutral, your climate is impacted by what everyone else is doing. So we all live with the net effect of everyone's greenhouse gas emissions. And because of this, global cooperation is the only solution where we can actually try to tackle what matters for climate change, which is the amount of carbon dioxide in the atmosphere. And that's how I see this local to global bridge through the International Year of Global Understanding. Thank you.